Sorry about interruption.
Okay. So generally, this type of research has two main outcomes, like one of two main outcomes. The first is checking for investigating the change in risk of adverse health outcomes due to either rising temperatures, or the second objective tends to be looking for the change in risk instead due to heat wave days compared to non-heat wave days. Both of these check the impact of heat. Some other studies, instead of looking at heat, investigate air pollution, such as ozone and particulate matter levels. This is not the focus of this presentation, but I want to say that because it tends to have the same analytic techniques involved. And some studies will investigate heat and air pollution at the same time. For those ones, it tends to be, like I mentioned, ozone levels, particulate matter, either PM10 or PM2.5. So common outcome data that's checked with for health outcomes. Typically, these are usually either mortality or morbidity. Mortality being measured actually as the number of deaths. Mobility can be measured in many ways. Common ways as measured include hospital admissions, so inpatients, emergency department admissions, ambulance call-outs, workers' injuries claims, and quality of life. There are some metrics that can combine both mortality and mobility, such as disease-adjusted life years. And these can be overall cause or disease-specific mortality and mobility. That is to say, it can be either like deaths or mobility due to just any cause during heat, or it can be from a specific disease cause. That heat-related illnesses are the disease group that we most associate with heat. However, it can also include those with an indirect relationship. Cardiovascular, or the heart, kidney health, and mental health tend to be more popularly researched and are known to have a strong association with mobility for heat. Whereas when you incorporate looking at mortality, that tends to be particularly the cardiovascular as well as respiratory, the lungs. Usually, these outcome data is retrieved from real-life world data sets. These studies tend to, as for heat, is usually very wide, focuses on the population as a whole. And to look at population data, you tend to look at population level data. So within Australia, some examples would be going to the Australian Bureau of Statistics for mortality data. You can go to the AIHW, Australian Institute of Health and Welfare, for hospital data, as well as mortality data. Sometimes you can, as well as usually individual state level health departments for hospital level records. Good. And then workers' injuries claims would be from Safe Work Australia. It is also possible to do smaller scale clinical laboratory trials or clinical trials looking at the adverse effects of health. These typically focus on the subpopulation and tend to focus more on physiological impacts and pathophysiology. Though we are not they tend to have different analytical techniques, and they're not going to be focused on this presentation. With this presentation focusing on population health, like population level analyses. These health outcomes are generally only available on a daily basis. That tends to be because they're either only recorded on a day-to-day basis, and exact time point identification of when they occur could lead to identification of patients or participants, and that would propose confidentiality results. Thus, these analyses tend to look at outcomes at a daily level. That will be either by aggregating the results to a data level or using models that will then assess at the individual record, but then present the results daily. These daily outcomes are then matched with corresponding daily temperature data. Temperature data can often be attained either daily or hourly, though if hourly, it would then be aggregated to a daily level for analyses. Well, some analysis you can also look at it weekly and monthly. Daily, though, is usually the norm. That's because if you then aggregate it to a weekly level further, you tend to less capture the variation over time, and you'll get a less accurate representation of the heat relationship. For example, if you have a warm weekly mean temperature, that could represent either warm days throughout the week or 4 hot days and 3 cool days. And whilst capturing it daily allows you to capture both the better reflect the maximum and minimum temperature. So looking at temperature, so usually we declare the outcomes to temperature. When looking at temperature, you can look at usually air temperature is the norm, and that's usually just what's reported like on our weather apps, like from either in the newspaper, on the website, or from the phone apps. That's most direct version of temperature. Some studies use apparent temperature. Apparent temperature is a combination metric in which it investigates air temperature, combining it with other climate variables, most often humidity. Some also add other variables such as wind speed and solar radiation. Temperature is generally analyzed continuously. So that means allows you to capture the full range of temperature. Rarely, some studies will categorize it. Temperature data is generally easier to obtain than health outcome data. It's often readily available online, publicly available, you can download it. The most common source in Australia tends to be the Bureau of Meteorology. If it's from a weather station data, you can usually download it straight from their website for temperature. You can also contact them to obtain more complicated data sets, such as gridded and satellite data. There are other websites as well. And some not just within Australia, but there are also international data sets for temperature available online. The other commonly assessed exposure is heat waves. This is a little bit less straightforward. Heat waves are commonly known as, internationally, as a prolonged period of high heat. So then when you want, for research purposes, you want to have a precise definition to be able to precisely say when a heat wave occurs and when a heat wave doesn't occur. This is easier said than done, as there's no strict international definition. The definition varies across different countries as well as studies. Often the definitions are categorical. The old Australian heatwave definition, I think in 2010, was either 3 consecutive days where maximum temperature exceeded 35 degrees. There are some continuous metrics. They're not that common. One of them, in the case of Australia, is the SS heat factor, which I'll talk about in a later slide. So there are other definitions. In fact, usually when countries don't have a categorical definition, like a national heatwave definition, they tend to make up their own definitions. They tend to be similar to the Australian ones, such as, for example, like a high temperature that is met over at least 2 consecutive days, with the durations varying. Some studies, some countries will have multiple definitions of heat waves to denote heat waves of different severities. For Australia in the past, the 3 consecutive days, that was their standard definition. They would have an alternate definition for severe heat waves, which was either 5 consecutive days where the maximum temperature exceeded 35 degrees, or 3 consecutive days where maximum temperature exceeded 40 degrees. These used to be the norm for Australian research, though they've now generally been replaced by excess heat factor within Australia. So this metric originated in 2009 in South Australia. It was later refined in 2013. And since then, it's been incorporated as the South Australian heatwave definition and was then later made the national Australian definition. And that's now the norm for Australian research for heat waves. It is sometimes used in other countries overseas, particularly for those with no national heatwave definition, as well as for some studies that are investigating the impact, like to see how excess heat factor would be incorporated into their system and if it would be useful. So since it's very relevant to Australia, I'm going to talk a bit more about the excess heat factor. It's not a straightforward definition. It's relatively more complicated. So the main metric used is daily mean temperature, which is the average of the daily maximum and minimum temperature. It comprises of 2 indexes, or excess heat indexes. The first is the significance index. This measures if the recent heat over the last 3 days is unusually hot. So for that, it looks at daily mean temperature averaged over 3 days and compares it to the 95th percentile of daily mean temperature over a set time period. So that set time period, but it usually and officially is the 95th percentile of daily mean temperature from 1971 to 2000. It's a 30-year period. That was chosen intentionally because 30 years is generally the norm, like internationally, and it's agreed by the World Meteorological Organization to be a long enough period to capture long-term effects of climate relatively stably. And 1971 to 2000 was used because that's considered a relatively stable period for Australian climate. Our definition uses for the 3-day average this day and then next 2 days. The reason it uses the next 2 days instead of the past 2 days is because this definition is used for forecasting purposes to predict when the heat waves are coming and to issue heat wave warnings. And for that forecast, they prefer to forecast to see how it will appear in the future. The second index for calculating EHF, that's the acclimatization index. That compares the most recent heat against semi-recent heat. It again uses the daily mean temperature averaged over 3 days and compares it to the preceding 30 days. Generally, heat adaptation, or like our adaptation to recent heat, is thought to take place within 2 to 6 weeks. And so for that purposes, we've then averaged that to a month. So then using those two indexes, EHF is calculated as the multiplication of the significance index and either the max of 1 or the acclimatization index. That has a few implications. So, which I'll show on the next slide. So most EHF, most EHF values are negative, and that's done intentionally. Negative values indicate it's not a heat wave day. And EHF values that are positive indicate heat wave days. We have an example here that from Adelaide where it starts generally negative, and then about the 25th of January 2009, the EHF value suddenly increases and then suddenly drops again, indicating a heat wave period. And that was a relatively large heat wave. And then there is a smaller heat wave from 4th of February to about 6th of February. So going back to the previous slide, you see here that for EHF to be positive, EHI sig, or the significance index, must be positive. So for that to occur, the 3-day average daily mean temperature must exceed the 95th percentile of temperature values. To get the usually more severe heat waves, you have to either have a large EHI significance value, but you also need a large acclimatization index. So that means usually you get the really high EHF values when the heat is both hot compared to the 95th percentile, but it's also hot compared to temperature within the last month. That leads to high, and that would commonly lead to a very high peak like this. EHF also denotes severe heat waves and extreme heat waves, in this case by the orange line and the red line. The orange line is equivalent to the 85th percentile of all positive EHF values, which in this case is about 30. And the extreme heat wave is 3 times that value. In this case, it's slightly above 90. EHF has a Pareto distribution. Most of the values tend to be quite small, in this case, usually quite negative. But then when you get it has quite a large right skew where EHF values can suddenly increase, as we can see with this large peak. So when we're trying to model our outcomes, we usually are modeling the health outcomes. These tend to be measured as a daily number or a count. That's to say, they're measured as non-negative integer values, 0, 1, 2, 3. So as I put the number of deaths, the number of hospital admissions. Usually there is dispersion. So we usually use models that account for the dispersion. Hence, for daily models, usually the quasi-Poisson or negative binomial distributions tend to be most common, as they are distribution suited for count variables whilst accounting for over-dispersion. You don't have to use these. Boston distributions tend to be commonly used as well if the degree of over-dispersion is acceptable, or they might use as well. Some models might use more individual level data, and they can use instead conditional logistic or Poisson distributions that tend to more natively incorporate dispersion. There's a few considerations to consider with the models. One of them is the confounding effect of the cold, as like we might have increased bad outcomes with heat, but you can also have increased bad outcomes from the effect of the cold, or you might have an improvement in outcomes. That tends to be very country specific, and both country specific as well as specific like health outcome and populations as to whether very cold temperatures have a negative or positive effect for heat on health outcomes. Sometimes the cold effect can actually be stronger than the heat effect. There's multiple ways to handle this. Probably a common one is to just restrict the analysis to use warmer temperatures. A common approach is to restrict to the warm season. In Australia, that is October to April. You might instead restrict your analysis to the summer period, or you might only assess temperature values above a threshold, such as the median. Restricting to warmer temperatures tends to be more common when assessing heat waves, where you're just looking at heat waves versus non-heat wave days, and then you remove the cold non-heat wave days. The other approach is to model both hot and cold effects in the same model. This is more common when assessing temperature, which allows you to capture the full range of temperature. It can technically be used when you use continuous metrics for heat waves as well, such as excess heat factor, although it is not the norm. Often with these models, heat is not, or temperature and heat waves is not the factor that has the strongest effect on the outcome, and these often need to be incorporated in covariates to effect. The big two variables would be time trends, including seasonality and day of the week. These often have a very large impact of health outcomes. For example, usually you tend to get less adverse health outcomes on weekends. It tends to be worse on the working days. And you also get very strong effects over time. This includes changes with the season, and also you get long-term trends. Long-term trends, usually from unspecified causes that we can't really predict. These could be multifactorial, such as changes in population size, changes in demographics, real-life phenomena such as epidemics, and also like improvements in healthcare. So we'll cover later how to incorporate and model those time trends. Other covariates that are commonly modeled include public holidays. These, like day of the weeks, can also impact health outcomes, often being lower on public holidays. Population size. Often population size is not mandatory, since if you don't model it, it tends to be captured in the long-term trends, but it can still be helpful to include that in the models. Humidity is known to impact the relationship between temperature and adverse health outcomes, so you can include it in the model to adjust for it. It's not strictly mandatory. Its impact varies more in other cities and countries than others. It tends to be less important in a city like Adelaide that is very dry and consistently dry, whereas in cities and countries where there's more humidity, such as Darwin and Singapore, is more important. Air pollution is sometimes modeled. It tends to be modeled more for countries and cities with a high air pollution. Australia has fairly low levels of air pollution, so it tends to generally not be included. But for countries with high air pollution levels, such as China, it tends to be more commonly introduced. This is not an exclusive list, and you can also include other covariates as you wish. For example, school holidays. Not a common covariate, but you can include that. So looking at long-term trend controls. So here's an example where they say like first image shows daily deaths over time. You can see there's a clear seasonal effect that tends to be higher around January, tends to drop around winter, and then to rise again in January, and that's consistent across the years. You also see a general change over time in which the number of daily deaths over time across each year tends to gradually, in this case, gradually lower over time. So, and in this below graph, this is for United Kingdom. You can also see daily trend, long-term trends in ozone with it changing over time. It's actually the inverse pattern where you see higher levels during, well, actually our winter, their summer in around June, and it tends to be lower in then January. And since this of the and this is very important to model this, otherwise you're going to have very biased estimates. So another impact is to be then say the lag effects, how to model lag, as heat on one day often has an impact over many days. The duration, for example, like you might have high temperature exposure one day, and that can carry through to multiple days. How long this impact tends to vary across studies' location, as well as health outcomes. It can be commonly from a few days up to 2 weeks for heat. And cold temperature, if it tends to be modeled, usually tends to have a longer lag period. That's commonly say 2 to 4, usually longer, commonly say 2 to 4 weeks. That tends to you also tend to need to model that. So how do we model the lag effects? So one way to model them is to then there's multiple ways to model lag. Individual models. You can do one way is to use individual models, one for each different lag period. You investigate one lag period at a time. Say one model for immediate heat, one model for heat 1 day ago, another model for 2 days ago, and so forth. This used to be done in the past. It's not common now. One common problem is that one is a lot more models. Two is that each model only considers the effect of that 1 day. Sometimes you get a phenomena from that when say you see increased association with heat in the most recent few days, but you actually see a negative impact in the next few days. That's a phenomenon called as harvesting, as what that tends to represent is when heat doesn't actually cause a new adverse health outcome, but it tends to bring it more forward. So you see negative further down and more further up. These individual models tend not to cover it. Another approach was done in the past was to just, instead of looking at them individually, was to combine them into one estimate. So say, here's a week, the effects over across that week, we're going to average that into one estimate. That tends to be not used now, as it tends to be considered to be biased, as it could treat each and every one of those days as having the exact same effect with little flexibility. Now we tend to move towards more flexible models. Distributed lag models is one, in which we'll then use a certain, it will actually incorporate each day set in a model. So that tends to be allow for more flexibility and tends to more accurately capture the change in lag over time. It does have some issues in which, by modeling all of them together, it can introduce collinearity, as the lag days tend to be highly collinear and related. And if you have particularly a lot of lag days and you're modeling all of them in the same model, you can get high collinearity, over-specified model, and you can get very imprecise models. We tend to approach that by introducing constraints on the models, like allowing more flexible modeling, such as, say, introducing a spline or function to allow us to more gradually capture the entire lag period without necessarily having a parameter for each day. Commonly, this is done in distributed lag nonlinear models. You can model the response linearly, but it's generally accepted to be nonlinear, such as with curves. And distributed lag nonlinear models is generally now considered the gold standard for modeling lag effects. Here's an example of how it will be modeled for different approaches. The first slide is using individual models, investigating one at a time. You can see that it tends to have quite high responses at the start, and then it'll start dropping afterwards. When you're modeling them all together, the effect tends to be more accurately captured across all of them, although it can be a bit more imprecise. When you use a constraint, like with a distributed lag nonlinear model, it tends to capture the effect more precisely. So DLNMs, generally accepted gold standard. They're flexible. Usually these are used for the main exposure, usually like temperature or heat waves. You can include multiple DLNMs in the same model. You can, for example, if you have an additional climate variable such as humidity, you can have both a distributed Lagrangian model for temperature and another one for humidity. This is a 3D representation of DLNMs to show what it looks like. As what they essentially model the health outcome measured as relative risk, in this case, against using both a temperature like exposure response relationship or temperature health relationship, as well as a lag response relationship. Using the three together, you get a 3D model that shows like the temperature effects and the lag effects. For example, at a value of set temperature value, there's this lag response and it changes over time. This can be quite difficult to read, so it can be also helpful to break this up into 2D plots. So the first four figures here, this shows at a certain lag value, say 0 days, 5 days, 15 days, 28 days. This is what the temperature response relationship looks like. And you can do the same for lag. Like at set temperature values, look to see how the lag response changes over time. One common trick is a technique used is to set, for example, we want to see, like, for example, like we want to affect temperature. We don't want to know just what the effect is at one particular lag day. We want to look at all the lag days go together into one estimate. You can then combine the relationship into one. So a cumulative, in this case, cumulative exposure response relationship, and that is the bottom figure. So this would say that this is the response over time. So saying that, so looking across the entire lag period, these are the impacts that we expect from temperature over time. These are what are most commonly presented in research, as usually it's the overall response we're more interested in. In terms of model families that we use, so commonly, since we're using modeling data with quasi-Poisson negative binary distributions, this tends to be generalized linear models with a log link used. This fairly stable, relatively straightforward, and you can interpret the results at relative risks, which tend to be easier to model. And these are usually more easily, and could be fairly straightforward to do on statistical software. Some studies will use generalized additive models instead. These use penalized regression models, and these usually allow more flexibility and they're usually more precise. However, they have a less clear model structure. That downside is that when you've been using multiple models, it can be hard to compare results across the models. Generalized linear models are the norm, though generalized additive models do have their advantages. Usually we model estimates as either relative risk, for example, risk at one value compared to another value. For example, we might compare the mean temperature to high temperature. And we might then, another example is, which has become quite common, is you look at the temperature value where the risk is at the lowest and you compare that towards other values. When looking at heat waves, you might look at heat wave days versus non-heat wave days. Commonly, relative risk may be converted to percentage change, and a formula here is, say, relative risk -1, and then multiply that by 100%. I wish there was money involved in this, but unfortunately there is not. Another common metric that's becoming increasingly common is attributable risk. Explain that. So attributable risk means the total risk attributable to exposure. Here's some basic equations for that up below. These assume no temporal relationship, no change over time. There's two metrics. The first is attributable fraction. This represents the sum of the relative risk values. So that would show, say, like, you're not just looking at relative risk at one point, but you're looking across the entire frame point. So and there's attributable numbers, which represents the number of cases attributable to the exposure, which is simply number of cases times by attributable fraction. Confidence intervals are not easily formulated with attributable fractions or numbers, especially. This is especially done when you're looking at temporal relationships, as usually when you have attributable risk with that factor in temporal relationships, you have considerably more complicated equations. For these, when you use, usually to generate composite intervals for attributable risk, we tend to use Monte Carlo simulations. So which is essentially we would then take the model out parameters, take the outputs, again the model data. We would then repeat that using like a subselection of that data, like remove a few values, repeat that a large number of times, often say 1,000, 2,000, or 5,000 times. Repeat it, look at all the estimates we get across those, and would form composite intervals by looking at the, say, the 2.5th percentile and the 97.5th percentile. That gives us a 95% composite intervals. And I'm just going to go through an example to show how this works. So this is an example from one of my studies. So this is looking at number of occupational injuries and illnesses attributable to heat waves. This was measured using excess heat factor as a continuous metric. So we've got excess heat factors as a histogram in the bottom. We can see there's a large peak, like most values are negative, and then there's a very sharp skew towards higher values, with EHF values getting very high. And this tends to be more common, quite common to see high EHF values in countries with fairly dry climates. So this is measured. It was measured the relative risk of converted to percentage change. The blue line here represents non-heat wave days. Once we hit the heat wave threshold, which is measured as EHF of 0, we start to see the number of cases gradually increasing. But this is for low intensity heat waves in orange. Red is for severe heat waves. Which means that like heat wave, I think the percentile for positive EHF, like 85th percentile for positive EHF value is about 40. And this is what I've defined a study as very severe heat waves, which is twice that value. So that shows a curvilinear relationship with as EHF value increases, the number of occupational injuries and illnesses gradually increases. Looking at that for attributable relative risk, we've used this model to then generate attributable fractions. So looking at all the relative risk values across, so from EHF 0 and above, we've estimated attributable risk to be fraction to be 0.14. That is saying that about 0.14% of occupational injuries and illnesses are attributable to heat waves, and that's with a confidence interval of 0.094 to 0.217. Although it sounds like a small percentage, that is across the entire period, so that over time represents a relatively large estimate. You notice that the estimates tend to be lower when you subdivide to low intensity heat waves, and then even lower for severe heat waves and extreme heat waves. This is because since it represents all the relative risk values that meet the criteria, you have a lot less days that meet the criteria for extreme heat waves, severe heat waves, and low intensity heat waves. So that means attributable fractions tend to be smaller. That's to say that only a small portion of injuries and illnesses are attributable to extreme heat waves because they are not common. They are quite rare. And as with low intensity heat waves, they're more common, so they represent a larger proportion. We also have attributable numbers, which is just basically timesing the attributable fractions by n, which creates over the time period. That starts the period with 13 years. We had about 15 for heat waves, and about close to 9 for low intensity, close to 5 for severe heat waves, and close to 2 for extreme heat waves. So additional statistical considerations. So just to go back, so when we discuss long-term trends, like how we model that, they're commonly modeled for splines, which are also commonly used to model exposure and lag response relationship with DLNMs. Splines allow flexible relationships, as it tends to vary over time, and you can place more knots to better define the structure at the expense of introducing more degrees of freedom. This represents that's statistical considerations in terms of where to choose your knots and how many parameters you want to include. And that affects exposure response relationship, lag response relationships, and long-term trends. Other ways you can model long-term trends include using time stratified strata, which is say that it will change for each combination of month and year. There is a choice then if you do that. What choice do you use? Like, is we going to do it for every month, or we're going to say do it every 2 weeks, every 6 weeks? Another decision is say with the length of the lag period, as like with heat, commonly short time. As usually with DLMs, you have to use the same lag period for both heat and cold if you're modeling the boat. So you want to say like, what is the lag period we're going to choose that's going to give us the best model estimate? And similarly, as well, that's also taking account the lag response relationship. It's not an easy decision. There's no straight way to do it. One way we commonly, there's usually the main considerations that we consider there is three. Well, one is, which is unfortunately not the side, is clinical considerations. What do we think is clinically more accurate? Statistically, we look at our AIC. That tends to be the main one, and looking at the residue checks. AIC tends to be used roughly as a model of AIC, as a model fit. So for that is for what we do here, say, is we want to look across different exposure response relationships, different spline fits. We would say fit one model using one predefined structure, would then repeat the model, changing the model structure slightly. Say like different extra knots, less knots, change or additional knots. Look at the AIC. Often would then tend to choose the model with the lower AIC. A lot of studies for sensitivity analysis, they'll look at all these models, they'll look at the AICs, they choose the one with the lowest AIC, and they present the results in supplementary material showing this is what the AIC, this is why we chose this model, this had the lowest AIC, and just to let you know what the estimates look like, these are what the estimates look like with those other models, and hopefully they are similar. They do usually tend to be similar. Whilst the AICs come, if you look at multiple models at the same time, like say you want to say model same response, but for multiple cities at the same time, you would then add the AIC across those models and then look at the minimum across them for each different model. Whilst you're doing that, it's still also important to look at your residual fits. Check, like, is the model capturing variation correctly? How is it adjusting for it? And is there any major issues that we need to look into or potentially correct? Next slide is, in the past, it was more common just to look at one city at once. Now with increasing data availability, studies getting more complicated, it's often more common to look at multiple locations simultaneously. For example, not just looking at Adelaide, but looking at Australia as a whole and looking at multiple cities. Generally, the two approaches there are either have one large, like the first approach would be one large model to look at everything together. That's say you include all the cities or areas within that model, and then you include different location as a fixed or random effect. Commonly, that would be a mixed model, where you say have a random effect location. It is, however, very computationally intensive and for usually when the focus is looking at how the daily variation, like for these type of studies, it's usually not the norm, partly because it's computation intensive, and partly because we tend to do the second approach, in which you model each individual location separately, then you combine the results using meta-analysis. This has some advantages. It tends to be less computationally intensive. You tend to get individual models that are more specific to each area, that just focus in the area. And then you can still use meta-analysis to introduce the different effects location. So you get combined estimates for all of them together. You can still include different covariates for each city, each location, like not just looking at city, but you can also say for very large studies, often you say you consider what's the temperature range across these cities, what's the mean temperature value in those cities, any demographic factors across the cities, and these can be included as meta-analytic variables, either fixed variables or mixed variables. What's also become common is particularly when you have a lot of studies including meta-analysis, you'd then arrive best linear unbiased predictors, or BLOOPs for short, and those will be then used as the individual model estimates. As they're thought generally are more precise, and therefore they tend to use information for the meta-analysis to give more precise, and often thought to be more often, but not necessarily always, but often more accurate. as it tends to use information from the meta-analysis. That's particularly helpful for the locations that, say, don't have a large population size, don't have many outcomes, they'll be quite weak in statistical power, and they can borrow information from the meta-analysis. Give an example, next slide. So this is two graphs here. So the first one is looking at, this is just study-specific estimates for Australian cities, well, or the capital cities is Canberra, and the one on the right is best linear unbiased estimates. So this one doesn't have constant diffuse, but you can see there's quite a lot of variation in them. When you use the bloops, one effect is that it tends to pull them more towards the overall effect estimate. In this case, the pooled effect is this black curved line. It's a bit more unpredictable in the study specific, and then they tend to be pooled more towards the overall response with the best linear unbiased predictors. In this same study, we tended to use the best linear unbiased predictors, and this is the results for Adelaide, Brisbane, Darwin, Hobart, Melbourne, Perth, and Sydney. We've seen relatively similar effects where we see, and this was actually still true even for the individual models, where we're generally seeing less injuries and illnesses in colder temperatures and more during hotter temperatures. And you do see temperature or heat wave variations, such as higher values for EHF during the more dry cities like Adelaide, Melbourne, Perth, where so the more humid cities, particularly, especially Darwin and Sydney, you get different heat wave patterns and you see lower EHF values. So that's looking at overall response. This is for the overall exposure response relationships. So this is the lag effects all pulled in together. So that's across the entire lag period, which for this study was 10 days. This is an overall exposure response. So this is the combined estimate from all those individual cities put into one curve. Other considerations with models is, for example, like if you have an outcome that looks at infectious diseases, often the results are correlated with each other. Like say with an epidemic of infectious disease, you might have an outbreak. You have a high amount of infectious diseases at one time, and more infectious diseases they spread. And this number tends to increase rapidly. And then once people's immunity starts to build, it then drops rapidly. Most outcomes do not have this level of high correlation, like heart disease, overall cause. Of course, generally you don't need to consider the autocorrelation, but for infectious diseases, where it's such highly correlated, you often need to use a model that does adjust for autocorrelation, such as autoregressive models. Another consideration is if you use although most of the health outcomes are count variables, this is not always the case. Cost, for example, where we look at, say, here's hospital admissions, here's health outcomes, what are the costs because of these health outcomes? Costs tend to take much larger numbers and it tends to be very highly skewed. You can have, and that can be usually really very high skewed. Often you might, account model distribution may not fit the data as well. You might need an outcome distribution that can better account for the large skew. Examples being like a gamma distribution, which takes more skew, or a Tweedy distribution, where a Tweedy distribution allows you to model days where there's no costs or no outcomes, which is a limitation of the gamma distribution. As I mentioned before, a lot of studies in the past would aggregate the results to make daily models. This is still commonly done. Some models will instead model the individual records using conditional logistic or Poisson models. These are more complicated to do and is a bit harder to work with, but this does let you better account for individual variation. Especially if, say, you have the same person who then presents over multiple days. We're starting to get increasing usage of Bayesian and machine learning approaches for these type of analysis. It's still fairly new and innovative, and computational power tends to be a very big burden here, as it tends to be, you require a lot of power and takes a lot longer. Especially, as often, which I've had a colleague that said it took him a month just to run a Bayesian analysis, like an individual record Bayesian model just for one city. So as computational power gets stronger, this is starting to get addressed. When the approach for meta-analysis, it can be quite complicated, taking a lot of information at once. One approach to adjust this is to use principal component analysis, which reduces the complexity for the meta-analysis whilst preserving most of the information. And common extra applications, which I won't go into in depth, is after we've modeled the individual location, this is what relative risk, attributable risk is for individual locations, is to project the results. Often projected to hypothetical future scenarios, which we know what it's like. This is what we're estimating currently. Now we're going to see what is it going to be like in the future. To say different scenarios with climate changes, further global warming, socioeconomic changes, or population scenarios. This tends to work by you take the exposure response relationship generated in a current data set and apply it to a future climate data set that simulates those future scenarios. And from that, even if you keep the exposure response relationship the same due to the change in the temperature values or heat wave values, you often get different attributable risk estimates. Another approach is area we're looking to is downscaling results, where you might analyze the main results might be done in larger areas where data is more readily available. But you might not be able to get data for very small areas because of very small population counts, confidentiality concerns, or you just don't have the comps for meaningful analysis. So another approach is say, again, take the results you get from the main models, exposure response relationships, or meta-analytic results, and then apply those to smaller areas so we can more precisely estimate what is the risk in these individual areas. So just summarize just a few points, focusing on population research, common research topic, investigating adverse health outcomes versus temperatures or heat waves. This is commonly assessed at the daily level due to data availability and awareness level. It's important statistical considerations to model, which is the impact of the cold, covariates, particularly long-term trends, also day of the week. And you need to consider what we expect the exposure response relationships to be, as well as what the lag response relationships to be. These are commonly presented as relative risks and attributable risks as useful estimates to show what is the risk for one value compared to another, and what is the overall cumulative risk, or how many cases and the risk attributable to heat. Thank you all for listening. Thank you for listening, and I'm happy to answer any questions you may have.
So thank you, Matthew, for the very comprehensive and topical talk. I know I've got lots of questions, but anybody in the audience, I'll repeat them for those online. I think we've got at least 3 questions online as well. Andrew, do you mind reading out the online questions? And then we've got one from Suzanne.
You've probably got access
Yeah.
there.
Yeah. If you scroll down,
there we go. That's the confounding one there.
Yeah. So in the sense that for that first question, the DLNMs tend to just expand the temperature lag response relationships. So that tends to model the temperature and lag more comprehensively.
People online don't know which one you're looking at. You'll need to read it out.
Okay.
Just read the question then.
Okay. So the question is, can confounding variables are incorporated in DLNM approaches like other ordinary logistic regression analysis? Answer is yes. Is that the covariates often then you tend not to include them directly in the DLNM proportion, but you tend to include them alongside it. So let me just share, I've got a few extra slides. So which I have here. So this is an example for a time series model. These outcome log EYI. And then TI would be the effect of heat, temperature or heat waves. If you use a DLNM, we would replace TI with the DLNM, as that puts the DLNM in. Other covariates can still be included alongside that. In this case, say we've got a spline to show for long-term trends in seasonality, a variable for public holidays, and a intercept. And likewise for these other model designs. Look at the next question is, James, how does quasi-Poisson compare with negative binomial? Are there criteria for choosing which to use? So brief answer is no. The quasi-Poisson and negative binomial distributions tend to operate very similarly and tend to give very similar estimates. It's the differences between the two often tend to be so minuscule they're usually not investigated. And usually people just use whichever is easier to use, which is based on how easy is the program. Most in R, it tends to be quasi-Poisson. That tends to be just because you can use the quasi-Poisson without packages. Whereas in, say, Stata and SAS, negative binomial is easier. That's one difference. There are notable differences between the two. Quasi-Poisson tends to be generally better for investigating values close to the mean. Negative binomial tends to be better at modeling for outliers by theory. And that's usually because of the equation where negative binomial has it as an additional intercept by squared. In practice, though, the differences tend again to be very small, and no one's going to criticize you if you only look at one of the two. Okay, the next question is Bayesian spatial temporal modeling considered the gold standard where the structure of the spatial and temporal units is considered? Spatial temporal model is quite common. Bayesian, I think, is generally considered to be at the stage. So as probably is overall, my opinion, I think it can be better than frequency statistics, but it is usually a lot more complicated to do, and it's not as considered necessary. And it also has additionally modeling complexities. Like it tends to be separate, more difficult to incorporate DLNMs within Bayesian modeling. So at the moment it's not usually I won't necessarily say it's thought of the gold standard, but if you can put it in, it's helpful. Arguably, I feel at the moment machine learning is getting quite hyped, and you could probably ask someone else. Some people won't say there's a gold standard whether you use frequency Bayesian or machine learning, though I think that is a moment bit subjective.
For our next question, we've got two in the audience. I think Suzanne and then.
I've got already about
right.
But negative binomial models. You already answered my question.
Yeah.
Thank you.
And Lynn also has a question.
Thanks, Matthew. I was just wanted to follow up on the spatio-temporal point, because I know that you talked about putting in location as a fixed or random effect in the models, but I've been trying to think about ways to actually recognise the geography in the nearest neighbour kind of sense in some related work, but haven't found much in the literature, and just wondered if there is much done where there's the temporal structure, but also recognising at an area level, say at SA3 or something, two adjacent areas might have similar outcomes, and there's some structure there that's not taken into account with a fixed or random effects, not recognising the distances. Is there anything you can point me to on that?
So for one of those online, the question's about using sort of nearest neighbour approaches for the geographic effect rather than the fixed and random effects.
Some studies do that, like they would consider like locations close by and incorporate that as either as a variable, or they'll actually say like there's correlation between the two. I haven't done it myself. I think it gets to be very complicated modeling. Some of the Bayesian spatial Bayesian or frequentists, I think, can do that.
Yeah, I'm just not hitting the right keywords. I'm sure there's literature, but I'm just haven't. Okay, thanks.
And Wayne?
Heat's pretty nasty, does kill people. I just wonder if you've captured the whole complexity of it. If things like the amount of air conditioning in a community, the amount of exercise people are doing, all that sort of stuff. You captured all that?
For the results.
So the question was about capturing other factors, say exercise or air conditioning at the individual level.
Usually those individual level records, they tend to be done more at studies at usually the individual, like smaller scale individual or clinical trials that we often look at the pathophysiology counts. For the population health studies, when you're aggregating results daily, it tends to be quite difficult since you don't get that individual data capture. the ones that model at the individual level and then project at the data results, like the conditional models, like we could do logistic and Poisson, can potentially capture it. The biggest difficulty, though, is actually having data to capture that records. As often said, like looking at population health data, you're often not going to know which of these patients are going to actually have been using air conditioning or not, and how much. So it tends to go missed. The Australian Bureau of Statistics does have a publicly available data set for air conditioning use at the state at the city level, but it's not at the individual record. Like for exercise, it's usually the same issue with air conditioning, which is hard to actually capture that at a population level.
So I think we've got time for one last question, and I've got a question which is very similar to the last one online, which is there are two effects really. There's like a physiological limit to heat, and there's also adaptation. So your excess heat sort of tries to take into account one, but again, have you looked at other measures which sort of take into account the physiological limit, like wet bulb, which also takes into account humidity, for example?
Yeah, so I'll address both the questions at the same time.
Yep.
There are studies, air temperature is usually the norm, but there are studies as well that use apparent temperature metrics, heat index, and wet bulb cold temperature. So in fact, for my PhD, I had used wet bulb cold temperature for some of my analysis. In terms of which to use, I think that is subjective. Like the approach is either you use that, if you want to look at those metrics, you can either use one combined metric to look at all of them, or you actually would model all those effects separately. Some studies people prefer just to use the one, like temperature, and then model the covariates. That's usually more common. And I think that's norm, and that probably does you use that way more model parameters. So you would probably be able to capture more variations in that sense. Like in this example, you might say like this is how temperature varies, and then this is how the effect of humidity, potentially wind speed, solar radiation, other variables, how they are modeled independently. One advantage of combining them into a apparent temperature metric, you'll reduce your parameters a lot, so more model simplicity. Though a downside is that metric, as they all have to increase as values to that metric, so you see less of the individual variation between how those metrics differ. Which one to use as well varies most often on the researcher, though the effect would also then probably vary between countries, cities, as well as what disease outcome you use. And this also probably depends on particularly like how humid it is in individual cities.
Okay, thank you, Matthew. I think that's it for the questions. Thanks again for your sharing your comprehensive knowledge and in-depth modelling, which I'm in awe of.